Hi, welcome to the Lecture 5 supplement in the Executive Black Belt course on probability distributions. If you're a black belt, if you're a green belt, you can get away with calculating probability by simply counting. For the most part, that's not going to lead you astray. If you do defects per million opportunities, or if you do a straight percentage, whatever is simpler, they both amount to about the same thing, which is just counting proportion of defects. If you're a black belt, a lot of times you can't get away with that. You're going to have to deal with small samples, and you're going to have to abstract a little bit more. We often, as a black belt, are confronted with things where we're looking for, in calculus, what Sir Isaac Newton would have said is the area under the curve. So just to give you an idea of what we're talking about here, let's see. Just to give you an idea of what we're talking about here, you know, if we have a particular distribution that, let's say we're looking at cycle times and we're trying to do the voice of the customer. Oh my gosh, what a terrible, let's see if I can erase that. Hey, look at that, I did. If we can look at a process that looks something like that with a customer spec of, say, here, and say we're looking at cycle times, right? If these are cycle times or delivery times or something like that, or turnaround times, whatever is the right in your vernacular, what we're really interested in is, you know, how do we estimate that area that's percent bad? Or for glass half full people, the percent on the other side. That's really what we're talking about with capability. So it's helpful to understand what are called probability distributions and some of the common ones in order to abstract this a little bit more, because in reality we don't usually see that. What we see is we see the histogram, right? We actually see the histogram when we do the data analysis and the data dump. We actually see the histogram, and we have to abstract, that's really that pencil curve, that smooth curve that fits that histogram is what's going to happen long term in this process. That's really what's going on long term. Okay? So what we're going to do in this section is really just take some time to understand what are some common probability distributions, how do we ask reasonable questions about them, and move on. And really it's just a question of recognizing some of the main ones. Okay? So we're going to do this in two different cases. One is for continuous data, and two is for discrete data. I can tell you that once you master probability distributions, it's not simply a question of, oh, I can calculate probability, but you can make all sorts of predictions, which is helpful, and lots of other different types of calculations that can go into business plans and things like that. So the better you get at this, the better it's going to improve all sorts of things that you can estimate and abstract. It's going to make you more of a painter with these mathematical tools rather than just a drafts person. Okay, but nuts and bolts first. Okay, so what's a distribution of a variable? So a distribution says these are all the possible values and the relative frequency of each of those values. That's really what a distribution is. So if we take a look at what that looks like on here, it's really just, if we can, again, abstract this, in reality, if we took more samples, it might look more like this smooth curve that I'm drawing. And you might ask the question, are there catalogs for that smooth curve? And it turns out that there are, that statisticians have come up with certain catalogs for things that already exist, and we can use those catalogs to do probability calculations. It's as simple as that. Here's what that long-term behavior might have looked like. I've drawn it in now using, instead of my pen, Minitab. Okay, what will we do with the distribution? So for right now, I want us to focus on essentially two questions. The first question we can ask is, given a probability distribution and a spec, calculate the area under the curve, under that probability distribution curve, on one or both sides, or calculate some area. So in other words, given that we have a cycle time spec of, let's say this is delivery, okay? Delivery time, for turnaround time for a delivery. Suppose that we have a customer spec of 11 days. We don't want it to be more than 11 days. We might ask the question, well, what percentage of the time are we less than 11 days? Let's estimate that long term, right? We may only have 5 or 6 data points. So I want to know, in the process that I'm designing, or in the process that exists, or in the process that somebody else has, and we have maybe 3 or 4 data points or 10, what's the probability that the next delivery is going to be less than 11 days? Or that if we do 50 more deliveries, what's the probability that we'll have 40 of them less than 11 days? We can answer that with a probability distribution. The other question is the opposite. Given I want to design a process that's going to meet this customer spec, say 40% of the time, what value should I give? What value should I tell the customer that we're going to be good 90% of the time or 80% of the time? Okay? So in other words, given this purple, let's say this is 60%, what is the point such that 60% is below that point? Okay, so those are the different types. And just in statistics, we call this a probability, and we call this the inverse probability. Okay, so if you're looking in Manytab, that's what you'll find. Okay, we're going to cover 4 continuous distributions, and continuous distributions look like this. It's things where you don't have to lift your pencil to make the distribution. Okay, those are going to be normal, the bell curve, log normal, which is a skewed distribution whose log is a normal distribution. So if you take the log of the data values, you get something that looks very normal. The exponential distribution and the Weibull distribution. Okay, so we'll cover those. Discretes are a little bit different, and we'll cover those too. But let's start out with the continuous ones, and I think you'll see that once you get one of them, they all work exactly the same way. All of them do. They're all exactly the same, which is cool. Now your question is just to say, which one of these models fits best in my situation? And before I want to go into this, before I really get, there's a pet peeve of mine. And one of the pet peeves when people say the data are normal, and I do it myself once in a while, so I'm not totally immune from this. But I want you to keep in mind, these are models. Okay? All real distributions are not normal. All real distributions are not log normal. Okay? They're abstract things that we use to say, I think the process is like this. And because they're easier to deal with than real data, you have to go out and collect it every time you want it. We can use these to generate data or to answer questions that we normally wouldn't be able to answer. But in the real world, no data are truly normal. Okay? They follow whatever their process is. And these are just abstract models that people have built. Let's say this is like, I don't know what happened to my screen there. There we go. I'm back. Okay, don't know what I did wrong or right there, but here I am back. Okay, so these are models. I think you got it. Okay, let's start with the normal distribution, and this is what it looks like. This is often called the bell curve. Many natural measurements and processes are associated with it. It has 2 parameters associated with it, and this is typical. Most distributions have parameters. Parameters are simply, they tell you essentially the specific type of shape that we have. So for example, let me see if I can go back to my drawing pad. I'm going here a little bit with some trepidation. For example, this normal distribution is different than this normal distribution, right? And they both are different from this normal distribution, okay? But they all of those things are normal distributions, okay? Important thing to keep in mind. I'm just going to see if I can go ahead and erase that. Not happening, I suppose. Okay. All right, there we go. Let me hide this again. All right, so let's do an example, and we're going to do it in Excel stats. And here I've got a cycle time that's distributed as a normal distribution with a mean of 10 and a standard deviation of 10 days. I'm sorry, with a mean of 10 days and a standard deviation of 1 day. And I want to know what is the probability that a randomly selected invoice will exceed that 11 days. What is the probability that a randomly selected invoice will take more than 11 days to send? That's the question I want to answer. Okay? So let's go ahead and answer that in Excel stats. And you can see here's the answer given right here, but I want to do it for you the first time. To do that, we can go to PDF either on our palette or more likely on here. So we're going to go to PDF, which stands for Probability Distribution Function. And I'm just going to leave this open the whole time. On this info page, you can see you can select all sorts of different things. I'm going to select normal. And all we really have to do in order for this to work, I'm going to blow this up just a little bit so we can see it a little better on our screens. There we go. Okay, there we go. Is enter in the mean that we want. So in this case, the mean is 10. I don't even have to change that. The standard deviation that we want, which I believe is 1. And then we want to enter the value of the variable, which is also 11 here. If we click on the shade, that's the picture of what we're looking for. And it'll actually, this shows us the probability that x is less than 11. Now coming down here, we can see that there are various things. This probability that cap x is less than little x is what we're looking for, and it says here 84%. Okay, so our answer here should be 84% of the time we would expect to be less than 11 with a mean of 10, standard deviation of 1. Now, we can actually check it in this case, and there's an interesting check. So I'm going to show you the quick check on my whiteboard here. And here's the quick check. The quick check is we know that if we look at a normal distribution, one of the properties of a normal distribution is, oh, that's a terrible normal distribution. Oh my gosh. I have to get better at drawing my normals. It's a very unnormal normal. We know that the area to the left of the normal is 50%, right, or 0.5. We know that because it's symmetric. It's supposed to be anyway. We also know, oh my God, this is even worse. We also know, let's see if I can do a little bit better on this one. Maybe I need to watch Dolly Madison or something like that. Okay, well, that's a little bit better, perhaps. We also know that within plus or minus 1 standard deviation, right, from the mean, which was 10, and this is 11, so that's 1 standard deviation. We know that that's 68%. So if the total here is 68%, this must be 34%, or 0.34. So our answer for this, for the whole thing, less than 11, right, must be 0.5 plus 0.34, and that's equal to 0.84. So in this case, we could actually check it, and it gives us the answer that we're looking for. Okay, let me get back to the slideshow here. And we can see that that's the probability that it's going to be less than that. So the probability that it's going to be greater than 11 days is 16%. Right? 0.158 is about 16%. Got it? So that's a probability that it will take slightly more than, or I shouldn't say slightly, more than 11 days. Could be quite a bit more than 11 days. Okay. Now, suppose we wanted to do something else. Suppose we wanted to say an invoicing process has a cycle time that's distributed as a normal distribution with mean of 10 and standard deviation 1 day. Again, it's the same as it was before. What's the 30th percentile of this? Or what is the point such that 30% of the time we are less than that value? We only meet, like if we wanted to do this, this cycle time and we said, well, we want to give you a guarantee that 30% of our deliveries will be less than this. What would be that? What would be the answer to that question? And we can say, if right here I've typed in 0.3, and there it is. It shows us there's our probability. So it says that we will deliver within 9.5 days, right? 9.47, 30% of the time. And if you do that, if you look at that, if we put in 9.47 right here, we can see that that makes a good deal of sense. You see that is about 30% of the time. Hopefully that's making some sense to you. If we wanted to see, well, what if we wanted to give a 90% guarantee? 90% of the time we will deliver less than X. What would that number be? Well, all we'd have to do is type in 0.9, and it says 11.2 days. Again, let's see if that's right. 11.2 days, and there it is. It says 90% of the time will be within that. How about 95? 95 is 11.6, and how about 99? There it is, 12.36. Okay, and it says that if we wanted to give a 99% guarantee, we could say this is going to be at your house within 13 days. Within 13 days. Okay. Hopefully it was helpful. You see you can play a lot around with this sort of things, and it can help you with goal setting. It can help you with estimating probabilities and things like that. All right? Now I will say there's one of the difficult things about this is that how do we decide it was a normal distribution in the first place? We'll have more to say at the end of the lecture on that. Just to give you an idea, on the bottom where it has extra tools, all of these have these extra tools where you can go between one value and another value, and that's all that this does on this page. It goes between one value and another. So if I want to go from say, this says 0 to 8 and then 12 to 20, what if I wanted to go from 0 to 10 and then 11 to 20? That gives me, multiple areas that I'm interested in. Okay? And if I wanted to do just something inside of that, like say 8 to 12, and then I'll just do 20 to 20 just to get rid of that. Change this from 0 to 20. There, it gives me something inside of that. All right, let's go back to our regularly scheduled program. So those are the two types of things that you can ask. You can say what's the probability that it's going to be above or below a certain value, and you can say what's the percentile. Okay, if I want to do a 95% guarantee or something like that, goal setting. Okay, now let's look into the log-normal distribution. I think you'll see that all of these work similarly. Here's what the log-normal distribution looks like. You can see it's a skewed distribution. The log-normal happens to be a very skewed distribution. It's very, very heavily skewed. Okay, its parameters are the mean and the standard deviation. Before I move on, I want to show you how this looks in the normal distribution when we move around the mean and the standard deviation. You can see how all these things change. Excel statistics is really good for that because you can do it quickly on the fly. And you can see what are the different shapes that you can do. Okay, we're going to do an example here. And in this case, it says that say it's a log-normal distribution where our parameters are 2 and 1. Okay, so the first parameter, which is the mean of the log, is 2, and the standard deviation is 1. And what's the probability that this company will not meet its guarantee? An in-house service guarantees the technician will show up within 24 hours of your call. What is the probability that they will not meet this guarantee? So let's go ahead and do that one. And then you can start from here and go to log normal. Enter in this one's a 2 and this is a 1. And we just want to know what's the probability that they will not meet 24 hours. This is all in hours. We want to spread this out a little bit. We can see more of the distribution. And there it is. It says the probability that it's above that. Let me shade that again. The probability that it's above 24, all this right here, not the purple but the white, all of that. Again, let me blow this up so we can see it a little better. Is 12%. So we're making this guarantee, and yet 12% of the time we're not meeting that guarantee. All right. So let's go back to. I want to for a moment show you that one of the things you can do with this. Let me unshade this. Is in Excel stats in this PDF is you can change around these values to see how that changes the distribution, what it looks like. So if we make this a 3, what happens to the distribution? Look at the right, and we'll see. Yeah, so it moves it out quite a bit. If we change, let me change this back to 2. If we change the standard deviation of the log, what happens? Let's double this. You can see that we actually we make it go way out. That's a 1. That's a 2. It changes the spread, you see. Okay. So it's still pretty inflexible. It's always a very skewed distribution. And that's what that looks like. However, let's take a look at the normal, and we didn't do this before. And I want to show you what happens when we change things like the mean. So I'm going to open up this a little bit so we can see. Hey, come on now. Let's go between 1 and, say, 40. Okay, so this is one with a mean of 10 and a standard deviation of 1. Let's change some of that. So let's see what happens when we change the mean. Let's change the mean from 10 to 20. And note what happens. Yes, so we call the mean a location parameter, and you can see why. If we change the mean, what's happening to the spread? Nothing. But the center is changing as we change the mean. Okay? On the other hand, what happens if we keep the mean the same and we change the standard deviation? If we make it tighter, we make it smaller, it tightens up. If we make it bigger, it spreads out. See that? Okay. Excellent. So that's what's happening as you increase the standard deviation, it spreads. If you change both of them, you're changing both of those characteristics. Okay, that's it. That's all I wanted to show you. Okay, let's go through a couple more examples. Let's take a look at, now you should notice that the calculations, as I say here, are generic. They're exactly the same techniques. So once you get one, it's just a question of which distribution do I want to use to model. The third one we're going to cover here is the exponential distribution, and this is often used when it's often used in reliability. So if you're looking at the lifetimes of things, like for example the lifetime of a customer, how long is this customer going to stay with you? That's often a good distribution to use, as well as if you want to see how long a light bulb is going to shine before burning out. So both of those things are there. It's also highly skewed, and the odd thing about this is it only has one parameter, the mean. Sometimes it's given as the failure rate, which is 1 over the mean. So you just have to kind of watch for that. Usually it's given as the mean of the distribution. Okay, let's do an example of that. Suppose that an average time for a car, it lasts 4 years, so its mean is 4.2, and is distributed approximately as an exponential distribution. Okay? So we know that the average time a certain tire lasts is 4.2 years. We want to ask, what's the chance that a new set of tires will last 3 years or less? So what's the chance that it will fail, its tires will need to be replaced in 3 years or less if the average time that it lasts is 4 years and the data are exponentially distributed? Okay, so that's the question that we want to answer, and let's walk through that. Okay, here we are. We're going to go to the exponential distribution. Again, I'll blow this up so we can see it a little bit better. First, let's play around a little bit with this. Let's change the failure rate. What happens if we increase the failure rate from, say, 0.15 to 0.5? Yeah, so it seems like it spreads out. I'm going to go from 0 to, say, 30 to spread it so we can see. What happens if I go to a failure rate of 1, double the failure rate? How about triple that? Yeah, so it's getting tighter. So as we shorten up the failure rate, you can see that it tends to spread out the distribution, which makes sense, right? If we have a smaller failure rate, products tend to last longer. Okay, so let's get back to our problem, and I have to admit I've forgotten it. So it's 4.2 failure rate, and I want to know how long it's going to last, 3 years or less. What's the probability that's 3 years or less? Less than or equal. Okay, so now this is the tricky part. So the 3 is easy. I'll put in the 3 there. That's my value of the variable that I care about. Let's shade that cumulative. There's my 3. The problem is getting the right distribution. So it said a mean time to failure of 4.2 is there. But what's the failure rate? Well, the failure rate turns out to be 1 over the mean, as I've given here in this formula right here. The failure rate is 1 over the mean. So let's put that in there. I'm just going to type it in directly. I'll put it equals 1 divided by 4.2. So if on average 4.2 is the thing, the failure rate is 1 over that average, and there it is, 0.23. And this tells me that the probability that I will have a 3-year or less tire is about 50%. So isn't that interesting that in this case the mean is 4.2, but the likelihood that you will be less than the mean is greater than 50%. That thought flies in the face of what a lot of people think of as average. So in this case, average is kind of atypical. It's kind of extreme, and that happens with skewed distributions because the higher data points are skewing or pulling that mean away from that center. Okay? So that's what's going on there. Okay, so there we go. So the chance that the tires will last 3 years or less, I've got the wrong thing circled on here. It should be the other one. I think there must be a slippage in terms of the little oval that I put in. But it should be 0.51 as I've indicated over here. So I've got the wrong thing circled, but that as you see it is 0.51, so a little bit greater than 50%. Let's look at our last distribution, and this is perhaps the weirdest one. It's called the Weibull Distribution. The parameters are a little bit weird, and we're going to rely on Minitab to help us with those parameters when we come to them. There are ways to figure them out. You can look at statistical books to do it, but we're going to use Minitab to help us, and I'll show you how in the end of the lecture. But the Weibull distribution is also used in lifetimes or reliability. The nice thing about it is it's very flexible, so it can be made to look like a normal distribution, or it can be made to look like an exponential distribution, which actually happens under some conditions. We're not going to go into that and do the calculation because it works exactly the same way, but just to give you an idea of the types of the types of shapes that you can have, let me just show you. So here's a typical sort of Weibull, and we can change the alpha value. So there it looks kind of like an exponential, doesn't it? That looks almost exactly like an exponential. Guess what it is? Okay, and let's make it a little bit greater. And look what happens when we make this even greater. Look, it almost looks like a normal distribution now, doesn't it? Very interesting. So it's very flexible. There's lots of things you can do with a Weibull distribution. You can't slice and dice your dinner, but there's lots of different things that you can do with that. And look what happens now. I'm going to make this fairly big. That was not what I wanted to do. Let me go from 0 to 5. Okay, there we go. Look what happens when I make alpha bigger than beta. Yeah, look what happens. You can't see it. There, I wanted to, oops, not 20. Let's go to 10. Yeah, look it. I'm even giving a bit of a left skew to this thing. You see that? You see that? Let's make this now 100, and that, yeah, that's maybe too much, but I'm giving this a left skew. Yeah, so it's pretty interesting how this can be flexible in terms of developing a number of different types of shapes. So Weibull can be a useful one. Tricky to estimate, though. Okay. So basically, I want us to remember again that these are just models. The data are never going to be exactly normal or exponential or whatever. So the steps are really to think about what logical data the shape of the distribution might be. For example, if you're thinking of, suppose you're collecting data on cycle times, there's no natural boundary on the left-hand side. A cycle time can be as long as possible. It could be a year. Like in some invoice things you'll find, yeah, there are some that are a year old if you're doing a receivables project. But generally speaking, many of these things have a left-hand limit of 0. So if you have something that has a left-hand limit of 0, that might indicate that you have a skewed distribution. So for example, many cycle time distributions are skewed. So it's important to think about that. Many manufacturing processes tend to be normal. Many lifetime or reliabilities might be exponential. So those are the types of things you start out with. If you have data, on the other hand, check the histogram and something called a probability plot. Now, if you're a black belt and we've gone through the capability, you'll know that there's something called a probability plot. You can do that in Minitab very easily. If you're a green belt and listening to this, you haven't done that. You should just use the histogram. And the third thing is just to try a few and see if you find a reasonable fit. And Minitab has a nice facility to help us with that. So let's do that. Let's try that, and we're going to look at the file distribution.xls, and we're going to use, let's use Minitab. Let's use Excel statistics first to do this and take a look at the histogram. And this is just tracking sales. Okay? So before we look into this, what might we think? Well, if I'm looking at sales, maybe I don't really know. Maybe sales sometimes are greater, maybe sometimes sales are less, or maybe this is a company that has a number of sales campaigns. Some they put a lot of money into, sometimes they put a little money into. So it's possible that I could get some skewed data. I better look at the histogram and see what makes sense. So let's do that. Let's do that soup to nuts, right? I say soup to nuts, but that reminds me of soup Nazi. I don't know why. It kind of sounds like that, I guess, the alliteration. Okay. Distribution 01, and here it is, sales in thousands of dollars, and we'll take a look at that in Excel statistics. Let's just take a, what I love about Excel statistics is you can do things pretty quickly. Oh my. I think it's pretty straightforward. This is a skewed distribution, right? Pretty clear that this is a skewed distribution. And the mean is 28. Standard deviation is 29. Okay, so we could use a few different fits. We could fit the exponential distribution if we wanted to. That might be a decent one. We might try the log normal if we look at maybe more classes of data. Log normal might be a good fit. Exponential might be okay. Let's go ahead and if we did the exponential, there's the mean, and we could do the failure rate, which would be above that, which would be 1 over that. So let's try doing that. That might give us a quick one. And we want to estimate the probability that this company will sell 45,000 or more a day, and the sales are already in thousands. Yes. Okay. So to do that, I'm writing down 28 or 20. I'm just going to call this 28.5. I think that's pretty close. Is my mean. And I'm going to use an exponential distribution to estimate what's the probability I'll have. Is it greater than 45? Yes, more than 45 in a day. So let's go to the exponential. My failure rate, in this case it's a success rate, but I have to enter in a failure rate, so it's 1 equals 1 divided by 28.5. And I want to know what's the probability that I'm above 45. And I better open this up a bit. There we go. And it looks like the probability that I'll be above 45 is fairly small, and it's given by 20%. So about 20% of the time, it looks like we're going to fail. I'm sorry, we're going to have 45,000 or more in sales. Hopefully that picture is helping quite a bit. Whoops, not that picture. But that picture is helping you quite a bit to visualize what makes sense and what doesn't. Okay, now let's do it using Minitab, and I'll show you Minitab has a little, has something that's helpful. You might have chosen a log normal, and if we chose log normal, well, that's okay, but we need to know the mean of the log and the standard deviation of the log, so we'll actually have to take the log of the data. We can do all this and get an answer, but it's a little bit painful. So I'm going to do this in Minitab, and we'll see, hopefully, that we get somewhat similar answer. Let's open it up in Minitab. You know, when we do the histogram in Minitab, it ought to look the same, right? Here it is right here. Copy this, go to Minitab, paste, and there it is. Let's take a look at the histogram. Do a fit. That's not it. Oops, that's not it either. There it is, distribution. Let's look at the exponential distribution. It's going to fit an exponential. Yeah, look at that. The exponential is not a bad fit. See that? That's pretty good. That is not a bad fit to this data. Okay. And it tells us there's our mean, 28.5. Okay, great. And using a probability plot, there it is right there, a probability plot. You can choose sales. I believe it's under labels. No, I'm sorry, I keep doing this. Scale. Oh. Distribution, yes, under distribution. That makes a lot of sense, right, Mark? Yes. We can do that. And here we're just going to use our crosshairs and go up to 45,000. Here it's a little bit hard to get it. Maybe I'm going to have to draw it exactly. There we go, 45. It's about, and it says it's about 81. So, you know, the answer that we got of 20%, it's going to be pretty close, right? So that was, again, that was a very close answer. If I actually ask it to do it exactly, where is that again? Yeah, there it is right there. Okay, I want to know not percentile lines, but the lines at the given data values of 45. Draw that in. Yeah, and there it is. There's my 70%. It says 79%, 79.3% is less. So that's very similar to my 20% is above, right? So it's not exactly the same, but I think if we looked into the PDF, it would be very, very close to that. So there you go. It tells you 45. This is predicting 45. The percentage of times that we exceed 45,000 in sales is about 20%. Now, what would happen if we chose a different distribution? I'll do the same thing, but now I'm going to choose the log normal. How would that differ? First of all, let's take a look at the histogram and see how it fits. Okay, so I'm going to do another histogram with fit, but now I'm going to do, that's what always kills me. It doesn't say distribution, it says data view. Yeah, and this might be a slightly better fit. Yeah, I kind of like that fit because it captures that stuff at the bottom. Exponential is not bad, certainly pretty quick. Let's see how much of a difference it makes. Here's a hint. It's not going to make that much of a difference because we're talking about that tail region where these two things, exponential and log normal, are basically the same. Okay, let's go back to our probability plot and see what we get when we do a log normal distribution. And And again, in this case, we say 18%. But the difference between 18% and 20% when we're doing estimation like this is probably not that great. Because remember, we're just fitting models. I would be inclined to go with this and to say it's a little bit less, that the exponential is being a little bit aggressive, and the log normal is a better fit. And so we'd go with that. To show you if you want to choose between competing fits and you've got Minitab, I find it to be very helpful. You got to be careful about playing this game, okay? Because I think the thought process that we just went through is a much more defensible one. And let's remember, these are all models. Tomorrow we're going to get different data, right? These are all processes. Tomorrow we'll get different data, and the fits may differ. So choosing a robust one that makes sense to us intuitively is often better than choosing, quote, mathematically the, quote, best, when they're all pretty good. However, having said that, Minitab does have a tool. It's in a weird place. If we go to Stat, Reliability and Survival, Distribution Analysis, Right Censoring, not right sensing, censoring, whatever that is, I know, but it's kind of weird that it's there. Okay, distribution ID plot, and we are going to specify, we're going to fit the Weibull, the log normal, the exponential, and the normal. Hey, it's just the ones that we have. We'll fit them all to this, and we'll see kind of which ones are decent fits. For now, wow, it looks like the Weibull is pretty good, but it doesn't get that top tail. And we care about that a lot. The exponential isn't good at the bottom, but it's not bad for the top. In fact, it's really good. The normal really is bad all over. But the log normal seems to be about the best. So we're going to go with log normal. In fact, log normal seems to be an absolutely excellent fit all over. So log normal would be the one of choice. If we're just worried about the question we have right now, exponential is good. We'd have to be concerned about making predictions in the low range, but in the high range, no problem, would work quite well for us. So again, log normal or exponential would be a reasonable choice for this one. Choosing log normal is certainly very reasonable. Okay, and in fact, if we here's the quote answers. If we choose a normal, it's a bad fit, and we're going to get a bad answer. The log normal gives us a very good answer. Exponential would have given us a good one too. Okay, so again, as a recap of all this, there's really only two questions that we need to answer, and you should note it's what probability is it that we would exceed or be less than a certain value given a certain distribution, like normal. Given a cycle time is normal, what's the probability that we have a cycle time that's greater than 12 days? Bam. Okay? And the other one is we can set goals. So we can say, okay, given that we have this normal distribution with a mean of 12 and a standard deviation of 3, what's the probability that if we give a 90%, where should we give our 95% guarantee? That sort of question can be answered. Okay, let's move into the discrete distributions, and hopefully we'll go pretty quickly through this. We're going to cover only two, and one is the binomial and one is the Poisson. You'll see that the Poisson is related to the exponential distribution, and so the game will be the same. For small values, it's going to matter, and we're going to have to care about whether it's discrete or not, but for large values, we're going to use a normal approximation. Okay. What's different about these is that a discrete distribution can only take on certain values. So, for example, what's the probability of having 3 or more spills in the office? Well, we aren't going to talk about 3.1. What's the probability of having 3.1 spills? There's no probability assigned to that. So, or you can think of if we roll a die, what's the probability that we roll a die and we get 3.5? It's 0. That's where we use a discrete. It can only take on certain values, certain individual values. The second thing I want to note is that unlike the previous one, we're going to rely much more on our intuition and our logical sense of which distribution should fit than we did in the previous case. All right, and the third thing is when our counts get large, we can use an appropriate continuous distribution. That's usually going to be the normal. Okay, First, let's go over the Poisson distribution. And Poisson means fish in French. I don't know why they chose that, but they did. Probably because it comes from a person's name. In fact, that is where it comes from. Okay, so this is appropriate when we have counts of defects. Okay, so if I measure defects, if I know how many defects there are, but I don't know how many non-defects there are. Typical example might be if I look at spills on the plant floor over the previous, or safety incidences on the plant floor over the last month, I found that there were 5. The previous month, I found that there were 3. I can't tell you how many non-spills there were, right? So we're counting rare events, usually of a defect nature. That's a good Poisson distribution, tells us something about that. The second thing is usually it works well when the count is rare. So in fact, Poisson distribution was developed literally to predict how many deaths I believe the Prussian army would suffer from mule kicks in the army. So they were trying to figure out, sort of like when we're predicting how many injuries are going to come from different places, turned out that the Poisson distribution fit that very, very well. It only has one parameter, and that's the mean of the distribution. Okay, it's very unusual in that the standard deviation actually equals the square root of the mean, which is rare. Okay, so we're going to do this, and we're going to use it in a practical way. Here we've got a company that tracks the number of gas leaks reported each week into its field service operations, and the data are given in distribution 2. And we want to estimate the probability that exactly 5 leaks will be called in next week, and then we want to estimate the probability that 5 or more leaks will be called in next week. So first thing, let's go to the tail of the tape, and let's take a look at the data. Data are usually very helpful, so let's go to that first. Here's our leak distribution, and you can see that if we use, I'm not going to use Excel statistics this time. I'm going to use Minitab, and I'll use what's called the dot plot. Get rid of that guy. Come back to our data, and I'm going to put in this for leaks, and we'll make a graph. If we do a histogram, the histogram will look kind of funny. Maybe it'll look kind of typical. See how it looks? I guess it looks kind of typical. But if we look at the dot plot, we're going to see something a little bit different. We're going to see that this only takes on certain values. Yeah. So look at that. There's no 3.5. There's no 2.5. There's no 2.4. There's only discrete values, right? So we want to know the probability that 5 or more leaks will happen. So let's take a look at that. Intuitively, we would expect it's sort of like the area under the curve above this normal distribution. So kind of like, maybe this area right here. If I paint this, it's kind of like I want to know if it's 5 or more. I would want to know. I'm not writing there. I guess I don't understand why it's not writing, but maybe Minitab can't do this. In any event, I want to know what's the probability that I'm on these guys right here. For 5 or more, it's that. For more than 5, it's 6, 7, 8, and 9. So you see it's less than that. Okay? So I might say that it's maybe for 5 or more, it's maybe 30%. For more than 5, it's a little bit less, maybe 20%. That's just taking a guess. Okay, so let's actually calculate that out. How do we do that? Well, the first thing we need to know is we need to know the mean, right? Because otherwise we can't calculate out what the mean is. Pretty straightforward. So let's display the descriptive statistics for leaks. And we see that the mean is 4.1. Now, if you're using Excel statistics, it's pretty straightforward. It is, let's close this down. It's pretty straightforward. Just going to select this and do a one-num analysis, and there it is, 4.1. That's my mean. By the way, I could have done the histogram. In this case, just left it like this. It leads me back to Excel statistics anyway. I love this program. Okay, 4.1 is the mean, and that's what we need, because here we said that the parameter is just the mean. That's all we need. So let's see what happens when we go to the PDF. And let's see if we can find it here. There's Poisson. Yeah, it says average number of events. That's the mean. It's at 4.1. Let's enter that in. And we wanted to know what's the probability of 5. Let's be very careful on this. First question is exactly 5 leaks will be called in next week. Ooh, okay. So what's the probability of exactly 5 leaks? So the probability of exactly 5 leaks is this. Okay, so it's exactly the height of this 5 right there, which is 0.16. So that's exactly 5 leaks. But now the question, the second part of the question was 5 or more leaks. And for 5 or more, that's K is greater than or equal to 5 or more would be 39%. The answer to the first one is exactly 5. The chances of getting exactly 5 are 16%. Chances of 5 or more is 40%. Okay? So that's it. It just adds up all of these different guys for you, all the way up to infinity in theory, but, you know, obviously real things don't go up to infinity. And that's it. So there we go. Those are the answers that we came up with, and you saw that I was doing it live right in front of your face. So now you know how to do it. The thing that you do first is you estimate your mean, and then once you've estimated the mean, you can plop that in, and you can ask lots of different probability questions about this. We could have done 2 or 5 or 10 or whatever. Okay. Now, one more thing I want to point out here is that if you type in 20, and you should do this on your own, generally speaking, when the mean number of defects gets to be about 20, a normal approximation tends to be really good. So that's another reason why it's really nice to use a normal distribution. Also very cool for understanding why an eye chart will work pretty well even when you have count data, as long as those counts are usually fairly high. If they're extremely rare, then maybe you're going to start to use something else called a C chart, but more on that later. Okay, let's move on and let's look toward the binomial distribution. So a binomial distribution is very, very similar to a Poisson distribution. What it differs in is that instead of just knowing how many defects we have, we know how many non-defects we have, right? So we can think of it as a coin flip. Anytime we flip a coin, we get one of 2 results. It's either a head or a tail, right? And we know the answers to both. So let me just give you an example. In the example of the safety incidences, and I said there were 5 safety incidences last week, how many non-safety incidences were there? You said, I don't know, can't tell. All right, well, if I flipped a coin 100 times and I said it came up 49 heads, you know for a fact that there were 51 tails, right? So I know how many. If a head is a defect, I'm just arbitrarily defining that, and I said I got 49 defects, you know that there would be 51 non-defects. That's the difference between a Poisson and a binomial setting. So an example in a binomial setting would be I made 50 deliveries. 40 of them were on time. 10 of them were not on time, right? I know both of those. Okay, that's a binomial setting. If you can abstract it as a coin flip, you can get it. So, so this is like a coin that could have any probability of coming up as a head. Maybe think of it that way. So it could have a 10% chance or an 8% chance or a 50% chance. All of those would be reasonable. Okay. Parameters in a binomial distribution are n and p, where n is the number of trials and p is the probability of success in each trial. So in the example I gave of 100 coin flips, n would be 100 and p would be 50%, 50-50 chance of a head. In the on-time delivery, it would be, I guess, 50 deliveries I had, n would be 50, and p would be, I'd have to get that from the data. If it was previously it was 80% of the time we delivered on time, then p would be 0.8. Okay. Let's do an example. Here's the 2 parameters of a mean and standard deviation of a binomial variable. Happens to be n times p and the square root of that right there. That doesn't come up too much. All right, so let's go back to an example. Here we have a company that selects 10 service requests each day and records can't get ins. The total numbers are given each day, so they do 10 a day. And I want to estimate the probability that exactly 3 CGIs will occur in the next set of 10. And I want to estimate the probability that 3 or less CGIs will occur in the next set of 10. So those are the two questions. All right. Here a success is a CGI. So let's take a look at that. If I look at the distribution, see I've got 10, I've got the number of samples. So essentially what I'm trying to do here is I'm going to try and estimate my average P, right? So what I could do is I could do a calculation here and say here's P, and it's 2 divided by 10, and so forth, and then do a one-num analysis on that, and that would tell me that P is about 0.21. Okay, so my estimate for P would be 0.21. That's for the whole process. You can see it varies once in a while. I could have also done it directly. There's distribution right here. I could have done it directly with this because they're all samples of 10 and just divide it by 10 at the end. It's 2.13. Divide that by 10, I get 0.21, right? No biggie. I like the previous one that I did actually, which was this. Okay, so I know long term my process is I have a 20% chance that I can't get in. Okay, so now let's go to our PDFs and let's solve the problems that we're looking. In the next set of 10, what's the probability that we get exactly 3? Or what's the probability that we get 3 or less? So let's answer both of those questions first, and then I want to show you what you can do with some of these. So we're going to go with binomial, and we have 10. I'm saying number of trials is 10, and my P was 0.213. And I want to know exactly 3. Here, let's make this big again. I want to know exactly 3, which is given by this. There it is, 21% chance that I'll have exactly 3. Can't get ins. And what's the probability that I have 3 or less? Yes, 3 or less. Can't get ins. And 3 or less would be 85% chance that I have 3 or less. Okay? I'll go to the slideshow just to make sure that we've gotten this right. Hey, look at that, we did. Thank goodness. Okay, so we got that right. So that tells me that, but I can also do things like capacity planning for this. For example, if I know that there are actually typically 200 visits every day, how many of those do I predict will be? What if I want to do my capacity planning for? Well, you know, let's assume worst case scenario. I want to staff so that on those 200, I want to staff so that I have, so I'm covering the risk of what if half of them are CGIs, right? So I might want to put in 100 here. What's the probability that I have 100 CGIs or less? Well, it turns out that it's pretty much guaranteed that I'll have less than 100. Well, what if you ask the question like, well, what's the probability that I have 40 or less? And there you go. So you can answer questions like that. 36% chance that I'll have 40 or less. And that can help me with capacity planning or what have you. It can also tell me if I'm doing, say, 2,000 of these a week, what would be the value of reducing it from the place where it is now to the place where it is later. I also want you to take a look at this. I'm gonna shorten the scale here. And I'm going to make it, say, from 30 to 40. And just to give you an idea, or 30 to 50. Let's go to 60. Just to give you an idea, look what's happening here. We actually are having something that looks more like a normal distribution. And as I said before, that happens. With small numbers, things like this don't look very normal. you can see it's skewed quite a bit to the right. I mean, yes, to the right. But as you increase the sample size or the number of trials, it does become fairly normal. In fact, the closest that it's going to be to normal is when it's 0.5. But you can see, even when it's not 0.5, when you raise the number of trials, it does tend to look like a normal distribution. Again, that's one of the reasons why an individual chart works well, even in a p-chart situation. Okay, so I want you to spend some time and write, in your view, what are the takeaways from this section, and what are the questions that you can answer. But let's take a moment to kind of summarize what we learned on our virtual Blackboard. So to quickly summarize what we learned on the virtual Blackboard is that sometimes when we have to estimate a capability and we can't simply estimate the capability, here's the VOC, right? When we have to estimate a capability and we can't just count. That's kind of the classical case where we have to, and we can't count, simply count, because either we don't have a lot of data or we want to predict things about the future. We're going to use distributions. Probability distributions. Okay? So that's the first point. Get that in your brain. That's a good place to do it. You can use it lots of other different places, but there are two types. There's what are called continuous and discrete. The continuous distributions are the normal, the log normal, the exponential, and we also touched base on the Weibull. Okay, those are the ones that we learned, and for the binomial and for the discrete, we learned binomial and Poisson. And remember, the two questions that you can really ask are, what's the area under the curve given x? Given x, what is this? Question mark, question mark. And the other question that you can give is, given this, what is the x that will give me that? Say 95%, I want to know the x that gives me that 95th percentile. Okay, those are the two questions that I can really ask. I can use probability distributions for making predictions of the future, doing capacity, as well as setting goals, as well as understanding my baseline capability. So lots of good stuff in there. We've just dipped our toes in it. Statisticians have cataloged dozens of useful probability distributions, but these four are very flexible and they'll get you a long way. Okay, so thanks a lot for listening. I do appreciate it, and we will call it a day. All right, see you.